Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, first off, I have to apologize. Usually I'm not the front man, I am the back-end programmer. The front man is Shantanu Jha, and he is at a different conference, so I am the poor replacement. I will make this as brief and painless as possible, I promise. So, essentially what we do is we want to study how do you safely sequester CO2, and why do you want to do that? And of course, the fact that you want to do something in the real world and you want to simulate it implies that you actually have to get data from the field. So your simulations, your reservoir characterization, your studies are data-driven from actual sensors in the field. First off, why do you want to sequester CO2? Well, it's very simple. We need energy. And to get energy, we burn fossil fuels. You can look at oil, coal, and gas, and they're the top three in terms of fuels that we consume in order to produce energy. And of course, this trend is increasing. It's unlikely that it will change until a couple of decades from now. Now, burning fossil fuels naturally lead to CO2, carbon dioxide. And you want to remove carbon dioxide from the atmosphere, or at least scrub it somehow, because it's a greenhouse gas. One of the ways you can do that is very simple. You sequester it in geologic formations. This is advantageous for many reasons. One of them is, well, you reduce CO2 emissions. At one stage, you actually might end up with carbon-neutral power plants that burn coal or oil or gas. The other thing is, if you sequester CO2, you can actually use it for enhanced oil recovery. You actually wash the rock clean of oil and gas by injecting lots and lots of carbon dioxide. Now, the geologic formations where you actually want to sequester CO2 in, they can have many characteristics, but most importantly, you want them to be able to hold carbon dioxide safely, environmentally, and geologically. Meaning you don't want the CO2 to actually change the formation drastically so it's unstable. You don't want sinkholes. And you don't want the rock to fracture, because that will lead to CO2 going places where it shouldn't. For example, the water table. Now, reservoirs that are depleted, as in you can't get any more oil and gas from them, they're very good candidates. Why? Very simple. They're porous. They can actually hold stuff underneath. They're impermeable to the surface, so if you pour down CO2, if you inject CO2, it won't bubble to the surface. The other thing is we already have a lot of existing infrastructure in terms of wells, tubing. And just to give you a perspective, typical wells, what we call vanilla wells, are 10,000 feet deep. The deepest well in the world is the Z11 well in Russia, and it's 37,000 feet. That's 7 miles. The well that Shell is drilling, actually right now, they're still drilling it, off the Gulf of Mexico, it's I think 20 miles off of Galveston, is 22,000 feet deep. They are going to lay down around 182 miles of piping just to produce that well. You can use the same infrastructure to actually inject CO2. So it's a lot of investment in hardware, just putting the tubing, the pumping stations, the separators on the ground, and you can use them, reuse them for CO2. The other thing is, we really know what those reservoirs look like because we spent lots of time and energy characterizing them. We run everything from well tests, pressure load-up tests. We do seismic, a lot of seismic over these wells, just to find out how far does the well go. Where should you inject? Where should you produce? How long should you inject? How long should you produce? What materials do you use? Do you use surfactants? Do you use enhanced oil recovery? What kind of rock it is? And all of this information is gathered, tabulated, and kept on record. For many people, the companies, the production company, and of course the US government, because they really want to know what you're doing there. All of this information that we gather is still very scarce. Usually your field extends miles in length and width and a few hundred feet, sometimes more, in depth. But what you get in terms of actual information is rather limited. We don't get a lot of rock cuttings from the formation underneath to the surface. We only get what we actually drill. So if you drill a hole that's this big, and let's say the formation is a few hundred feet. A few hundred feet multiplied by a diameter on an area of a circle, let's say a couple of feet in diameter, that's all the rock cuttings that you get to the surface. And a lot of it is deformed by the time it actually gets to the surface because you're circulating mud, you change properties because of heat, because of pressure. Moreover, you can actually do core samples. You can actually lower tools that eat away at the rock and then pull them up. And you can examine the rock and you actually see what it looks like. Coring, as you can imagine, is very expensive, and you cannot do it in oil-based muds. So a lot of time in the deep wells, it cannot be done. We don't have a lot of information to go by. So how do we characterize the actual reservoir? We do history matching. We don't run one reservoir model. We run hundreds. And we try to match what those reservoir models give us in terms of production, in terms of oil flow rate, water flow rate, pressures, with the actual production we see from the field. And that's how we know those models are relatively accurate. How do we do the history matching? Well, many tools are available. One really nice approach is the use of ensemble Kalman filters. These are the same ensemble Kalman filters you can use for radar systems. You can use them for hurricane tracking. You can also use them for reservoir history matching. So you start off with lots and lots of ensembles, lots and lots of models for the reservoir. And you run them. And you hit a time where you actually have production data. Usually for vanilla type reservoirs, that's every week. You have pressure readings from the actual wellhead, let's say. You compare your models, what the models say you should have in terms of pressures, flow rates, bottom hole pressures, compositions, etc., with what you actually get from the field. Based on that, you modify your models so that they adhere more closely to the actual production. And you repeat this for the history, for as long as you have historical data of the actual reservoir. This is essentially what it looks like. You have model generation, that's when you start, and you generate statistically plausible models. You don't want rock formations that are impossible because obviously that defeats the purpose. You have various models that have different runtimes. Once you have a historical data point that you can assimilate data at, you have a global reduction operation where you actually compute the Kalman gain matrix. You change your models so the runtime characteristics of those models change, and then you repeat. Now, to do all of this, you need a few tools. The tools obviously are, first off, you need a reservoir simulator, or two. In our case, we need two for various reasons. We use PETSI, the Portable Extensible Toolkit for Scientific Computing. Think of it as a solver library, and we'll revisit it in a bit more detail later on. We use reservoir simulators. We need reservoir simulators, so we write them, and we use them on high-performance computing resources, that is, parallel machines, supercomputers. And we have two reservoir simulators. We have Cactus Black Oil, that is based on the PETSI Portable Extensible Toolkit for Scientific Computing package, and the Cactus Code framework for high-performance scientific computing. And, of course, Defiant, which is based purely on PETSI. You also need the actual ensemble Kalman filter, the piece of code that computes the Kalman gain matrix. And we've written that because it's very simple linear algebra. We've written that in PETSI because PETSI handles linear algebra in parallel, so that's advantageous. And we need a way of launching those models, collecting the data whenever we have historical data point, and launching them again. And if they are run on separate machines, pooling all this data or transmitting it somehow to one local resource where you actually have all the data available. You can run the Kalman filter and spread them out once the Kalman filter step is done. So you need a workflow manager. For that, we used a Saga-based fault-tolerant autonomic workflow manager. And why is it fault-tolerant? Well, very simple. When you run, typically we run around 200 ensembles, each running on anywhere between 16 to 64 cores, and we submit them to various supercomputers. Almost always you'll have one job that runs over the queue time that is estimated, and it gets killed. And you don't want to lose jobs along the way. You want everything to be there at the end, so it has to be fault-tolerant. The last thing you need is a way of getting data from the field to your actual simulation. That's why we use a sensors to simulations framework that we developed back in 2007. Essentially, think of it as sensors streaming data to a data spool, which is, in our case, a MySQL database, using the ProdML, the production ML markup markup language, which is standard for the oil industry. And we query the actual production data whenever we can from the Ensemble Common Filter. And more on that later. So these are the tools that we had to develop to be able to do this. And this is what the closed loop actually looks like. We have the job manager. It launches the simulations. And if we actually have production data to assimilate and use in the common gain matrix calculation, we actually get it. We get it from sensors that actually collect from various sensors in the field. The building blocks that we use for all these tools are as follows. We use a portable, modular, extensible, high-performance computing framework, the Cactus Code framework, because, as you can imagine, we need geochemists, geologists, reservoir engineers. All of those need to be able to sit down at the same table and work together. It's very hard unless you have a common platform that everybody can use. We use PETSI because it provides us with parallel linear algebra, provides us with solvers, preconditioners, and interfaces to various other packages. For example, if we wanted to use algebraic multigrid, we can use the Boomer AMG package from Hyper underneath a PETSI interface to Hyper. And last but not least, we need an interface, a grid interface that allows us to use different resources that can be distributed, can be non-local, can have different architectures, and be able to transfer files across those different systems and tell an advert service, we have new data, we don't have new data, we have to redo a couple of simulations because they failed. All of that is provided through Saga, the simple API for grid applications. Now, sample results, I promise I won't dwell terribly on this. This is a simulation of an actual sand tank that we have at the back of the petroleum engineering department at LSU. It's an actual sand tank, just big box with sand, sensors on top, sensors at the bottom. And what we're doing is we actually filled it with water and we're draining the water. And we actually calibrate our models based on real live data that we stream through LabVIEW from the actual tank. Various calibration studies, and of course the case that we're currently solving, the SPE10 problem. This is an SPE10, a comparative study problem for Society Petroleum Engineers. And it's a layered reservoir, very heterogeneous, very anisotropic, and we're trying to inject CO2 at the four corners, and we're trying to produce as much oil as possible from the center. Once we produce less than 5% oil, we shut it off, and we keep injecting CO2 until the actual formation fractures. Obviously, we don't wait until it fractures. We stop about 50% the way there. A little bit more on Saga because I hazard a guess that's what a lot of people are interested in. Saga, the simple API for grid applications. It is a new way to develop applications in a sense that it allows programmers, software engineers, people like me, to add grid tools and make their applications grid-enabled and add some autonomic behavior to their applications without having to deal with Globus, really complex APIs, and, sorry to say this, Java. It allows me to use all sorts of tools and technologies that I need. Everything from transferring files across machines inherently, launching jobs remotely, doing everything that the grid offers with a very simple API. Furthermore, it actually allows me to do something more. It allows me to run on Condor. It also allows me to run on the Amazon EC2. And if anybody was wondering, had to spend $1,402 on the Amazon EC2. And I still haven't been reimbursed. Anyways, this is what it looks like architecturally. You have the Saga runtime engine, the C++ API, the Python API wrapper, and the C API wrapper. And currently what I work with is the Python API wrapper because it's very small, it's very compact, and it's portable. You just move it anywhere where you have a Saga installation. Now this is a run that is very interesting. We first started with saying, okay, we have various computing resources. We have Ranger Attack, where I work. We have Queen Bee at CCT, which is the place I used to work. And we have Abe at NCSA. And we thought, let's try to launch on all those three machines together and see if we can get any performance boost. And lo and behold, we actually do. So if we launch on Ranger alone, it takes us about 4,700 seconds to finish 100 simulations, 5 assimilation stages, and 8 cores per simulation. If we launch on Queen Bee alone, it takes us obviously more. And if we, well, we don't have Abe alone. But if we launch on Ranger and Queen Bee, it takes us significantly less than Ranger alone and Queen Bee alone. Furthermore, if we launch on Ranger, Queen Bee, and Abe, we actually get to the total time, we actually get a lower total time to completion. One thing we can also use is the batch queue prediction system, which allows us to trick the submission environment to thinking that we're submitting jobs that are optimal and should be run immediately. Obviously, system administrators were not very happy when we told them that this is what we were doing. We were really jumping the queues, submitting jobs that are tailored, just explicitly tailored, to run ahead of everybody else because they were short in size and they were large in duration. And we actually got really good results. We actually got improvement using Ranger, Queen Bee, and Abe with BQP because we don't spend any time in the queue. Now, this is not terribly interesting for CO2 sequestration, but when you think about it, for critical applications where you actually have something critical happening, you have a sudden loss of pressure in CO2. You're injecting CO2 and suddenly from 5,000 psi at the injector, you drop down to 2,500 psi. What just happened? You want to know where the CO2 went. You want to know if you fractured the rock and you're injecting CO2 in the water table. Because what you're doing is you're turning the water acidic. And you don't want to do that with fresh water. And in the end of the day, it really is just a matter of scale. This is the SPE 10 problem again. Suppose we have, this actually has 1.2 million cells, but suppose it has 1 million grid cells. And we have to use finite differences, by the way, because oil and gas industry does not believe in finite elements, finite volume, or discontinuous color, or anything else. They want finite differences. They can understand that, so we do finite differences. So 1.2 million grid cells. They don't understand adaptive mesh refinement either, so we can't reduce the number of grid cells. 1.2 million grid cells. 1,000 ensembles. That's 1 billion degrees of freedom. That's a lot of degrees of freedom to solve in one big dense matrix. That is the ensemble common gain matrix. How do we do it? Well, we parallelize everything. And we try to scale out as much as possible. So we base our code on existing tools that we know should scale. And we keep doing that, whether scaling in HPC resources or high throughput computing resources. Now, when I actually first started doing this, the guys started to laugh at me because it's, well, it's still not 1,000, but still that it gets the idea across. Conclusions. Well, very simply, we need abstractions because we need to do things on a higher level than we otherwise would. We need parallel linear algebra because dealing with 1 billion degrees of freedom is hard, and obviously you need parallel computing. Nobody will love you for running something that takes 1 billion degrees of freedom out of core on any of their machines. You need parallel reservoir simulators because you want to reach your result. You want a reduced total time to completion. So you have to use something that runs fast. You want distributed, high throughput, high throughput capable, fault tolerant, autonomic, and optimized frameworks for job managing, bookkeeping, keeping tabs on where the simulations went. All of these tools we developed. In addition, you also need other tools that we don't have. Tools that do, for example, geochemical interaction of CO2 with brine. Currently, we actually have a team of people working on this, and so far they're using Cactus. They're not terribly happy. They can't get their chemical reactions to work properly in parallel. We will always have work to do in terms of improving the simulations, improving the common gain. Currently, for example, the ensemble common filter works very nicely for very linear problems. Once you hit a binomial function, let's say the Buckley-Leverett problem in petroleum engineering, or a place where you have sharp drop-offs, or multi-component fluid flow, you have a problem, because the ensemble common filter won't be able to isolate the covariance matrices very clearly. You have to use something like an iterative, randomized maximum likelihood filter. It gets even more involved, more complex. So work is in progress, and we're still going to do more. In terms of launching capability, we can launch on TeraGrid resources. We can launch on Condor pools at Purdue, at Ranger, at Queen Bee. And we actually launched on EC2 and Eucalyptus at Indiana and at Amazon EC2. Any questions? I will even take Star Trek trivia.
I have a question about the use of Amazon EC2. Obviously, there's a cost aspect to it, which maybe
Absolutely.
Ways, but what would be the advantage that the commercial cloud like that would provide?
Sadly, none. We were just pressed for time, and we thought, well, how do we do this quickly? And we didn't spend enough time investigating where to run it. So it's sort of the effort sort of mushroomed out of control. We started using the Indiana Eucalyptus cluster soon afterwards, but by the time we actually moved to Eucalyptus, the damage was done, and my credit card was billed. So there wasn't much that can be done. In all honesty, one of the things that we want to look at is the use of, well, so in cloud computing, we actually did, in the cloud computing paper that we published about this effort, we used various modes of usage for the EC2, for clouds in general, as accelerators to help move the simulations along. Let's say if for some reason the NOAA guys decided to run on Ranger and you're waiting up in the queue, you start a couple of EC2 instances and you just get stuff done while you're waiting. And you have an estimate on how much a job will take based on previous history of the job. So you can get started with the low-cost, low-hanging fruit on the cloud before you start on the HPC resources. The other one was the use of clouds as fault-tolerant mechanisms. So if something dies on the TeraGrid and you want to launch it again, it will spend time on the queue in TeraGrid. You just launch it on the cloud. With all of this, and of course, in terms of cost, if it costs you a lot of money to launch on the TeraGrid, you just launch it on EC2. All of this taken into consideration, having a commercial cloud is nice and everything, but ideally, you want it done with a lower cost. So if the solution is critical, if you need it now, forking off the money to actually get the solution right now is worth it. Especially if you have, let's say, an environmental crisis on your hands. And of course, then you can have the Spruce guys calling and saying, well, why don't you use Spruce and tokens for instant-on computing? And that's a valid point. So the technologies that we can use are, well, there's plenty of them. And making the right decision sometimes can be a daunting task.
Any other questions? Well, thank you very much.
Thank you.